Hello, Saddleback College Robotics is proud to present our 7th generation rover, Prometheus. We are organized into 4 sub-teams: mechanical, electrical, programming, and science.
Our chassis is constructed of welded aluminum tubing with removable panels to protect interior components. The chassis features a machine belly pan capable of housing electronics in numerous configurations. Prometheus is powered by two 24-volt batteries connected in parallel, enabling long run times. The drive system is built around a custom control arm suspension with adjustable pneumatic shocks, providing resilience during missions across rough terrains. Prometheus's 14-inch 3D printed wheels, paired with a custom wheel hub and bearing blocks, balance both durability and flexibility while maintaining a low weight.
The electrical system on Prometheus features many advances in organization and design. Within the rover chassis, our custom power distribution board delivers power via mechanical relays and is able to supply 12 and 24-volt rails to onboard electronics. This year, we have redesigned custom PCBs, each for the ARM and science payloads, to further simplify Prometheus's electrical hierarchy. All our PCBs are designed with fuse protection and live telemetry for monitoring power. Robust communication throughout Prometheus is achieved by using CAN bus for our drive system and UART for the ARM and science payloads. Our use of wiring harnesses greatly simplify hardware integration and maintenance. In an emergency, pressing the accessible kill switch disconnects the battery and shuts off all power.
Prometheus's 6th degree of freedom arm implements brushless motors for high torque density. The first 3 axes of the arm utilize strain-wave gearboxes with custom-designed housing for minimum backlash on high-load joints. The final 3 axes use custom cyclodal gearboxes for high torque and zero backdrivability. Relative and absolute encoding on every axis allows precise inverse kinematics for ease of operation. Rigid aluminum tubing allows the arm to easily lift loads of 5 kilograms. With our mission-equivalent rocket ship, the arm has been tested for fine movements. Our lead screw-driven end effector features textured neoprene grips to securely pick up objects, operate joysticks, flip switches, and open cabinets and drawers. It houses a small linear actuator for precisely pressing buttons. 4 unique camera views give operators great spatial awareness. 2 of these camera views serve to provide a precise relative location of the mounted keyboard for the ability to perform autonomous keyboard input.
Communication with the rover utilizes a point-to-point wireless network bridge running on a 2.4 GHz radio band. ROS2, alongside its underlying middleware, FastEDS, is used as a communication framework to enable the control of systems on board the rover, as well as to facilitate the transmission of telemetry back to base station. Telemetry, including system status and logs, the startup and shutdown of individual subsystems, as well as the control of the science and autonomy subsystems, is viewed with a custom-designed web interface. Manual control of the arm and drive systems utilize separate gamepad controllers to provide better handling of each individual subsystem. Autonomous navigation this year is achieved via a custom solution featuring GNSS waypoint traversal and real-time obstacle avoidance. Our solution makes use of 2D LiDAR point cloud data to enable object detection. Precise localization is achieved using a differential GNSS RTK approach, giving centimeter-level accuracy. Operators at base station can set GNSS waypoints on an interactive map using the ROS2 MapViz package. Additionally, latitude-longitude coordinate pairs and a search action to perform upon arrival may be input to our custom GUI as an autonomous navigation action command. Our rover's depth-sensing stereo camera is used for autonomous detection of Aruco tags and objects. Recognition of water bottles and mallets is facilitated by a custom-trained neural network model. Each of these frameworks is tightly integrated with ROS2 packages for coordinate transformations and behavioral control. Additionally, a much greater focus has been placed this year on full virtual simulation of the rover. This has served well to expedite our testing and deployment process, especially with regards to autonomous navigation.
This year, our science payload is dedicated to identifying the presence of an unambiguous sign of extant life through the analysis of subsurface samples. Sites will be selected based on various habitability criteria, from geological signatures captured by our mass cam. Using an auger, samples are channeled into separate containers with independently controlled lids, capable of rejecting soil from above 10 centimeters and caching a subsurface return sample. Soil reserved for further examination will be washed, and the resultant liquid is dispensed into a light-tight housing. Through an ultra-sensitive fluorescent probing technique, the emission spectra of trace amounts of double-stranded DNA in impure conditions can be rapidly detected using a spectrophotometer. Additionally, the payload is equipped with a probe designed to measure in situ temperature and moisture levels.